Welcome to video instruction on continuity. To begin, you should have already filled in some very informal ideas about the idea of a function being continuous at a point x equals c. So there are no jumps, holes, or gaps in the function at c, and you can draw right through it without lifting your pencil. Okay, so the beginning of this video, we're going to go through somewhat of an activity that allows you to practice writing notation on limits, practice hearing it and writing it, practice putting it into a graph, and also building the concept of continuity. So the way it's going to go is that I'm going to provide some verbal information about a graph, and you're going to write it down from me saying it, and then sketch a graph that fits the criteria that's mentioned. So to start off, I'm going to do case one kind of just all together, and then we'll move on to case two and give you the opportunity to practice this. So what I'll do is I'll give information in this way. So in case one, there's going to be three pieces of information. First one is that f of c is equal to L. And then the second one is that the limit as x approaches c from the right of f of x is equal to m. And the last piece of information is that the limit as x approaches c from the left of f of x is equal to n. Okay, so I will give that information verbally. You will practice writing in just like I did, and then you're going to read this information and create the graph. So first of all, it says f of c is equal to L. So here's where c is. L right here means we have a point right there. So that takes care of that piece of information. The limit as x approaches c from the right, so coming in from this direction, then your function is approaching m. Now it does not equal m because it already equals L at c, so we'll put an open circle right there, and you can have any continuous flow of points leading up to that. The next piece is coming in from the left, and your function is going to go towards n. So the n, again, has an open circle, and we can do whatever we want as a piecewise function. I'm just going to do that. So then what we're going to do is determine, is this particular function that I've described continuous at c? And you can see that if you follow this, you would have to pick up your pencil to put this dot and then continue on. So there's a jump in between there, so it is not continuous. And we'll just write this up here, not continuous. And I'm going to abbreviate continuous because that's what math teachers do, at x equals c. Okay, so now here's what I'm going to do. I'm going to state the information. There's two pieces of information, so you can make sure you write it correctly. First piece of information is that, write it down as I say it, f of c equals m. f of c equals m. Second piece of information, the limit as x approaches c of f of x equals L. So those are your two pieces of information. I'm going to pause the video, and you should pause as well, and sketch in the graph, and when I come back, it'll all be filled in. So make sure to pause now. Okay, so I am back. You should have these things written with correct notation, and you should have something similar. It doesn't have to be linear. It could have done anything where you have a hole at c, and then you have the value of the actual value of the point at c is way up here. So now, is this function continuous at c? Nope, because we would have to lift our pencil. There's a hole, so we will say not continuous at x equals c. And from now on, we can just say no or yes if you'd like. Okay, ready? Case number 3. There are 3 pieces of information. The first piece of information is that f of c is not defined. f of c is not defined. Second piece, the limit as x approaches c from the left of f of x goes to infinity. And the third piece of information, the limit as x approaches c from the right of f of x goes to negative infinity. So as it approaches from the left, goes to infinity, approaching from the right, goes to negative infinity. Okay, I'm going to pause the video, and you can come back to check your work. Pausing now. Okay, we're back. So check your writing and check your graph. Should look something similar to this. And is this then, this function f, is it continuous at c? And the answer is nope, it is not. There's definitely a break in between, right? Okay, I think you're getting the hang of it now. Let's go. Case number 4. Here's your information. F of c is equal to m, as in Mary. The limit as x approaches c from the left of f of x equals m, as in Mary as well. The limit, or the third piece of information, is the limit as x approaches c from the right of f of x is equal to n, as in Nancy. Okay, I'm going to pause the video now. I am back. Check your work, check your notation, check your graph. Is it continuous? No, not continuous again. All right, is it ever going to be continuous? Maybe. All right, fifth case, we've got f of c. Oh, don't write it down. F of c is not defined, is the first piece of information. And the second piece of information is that the limit as x approaches c of f of x is equal to n. All right, I'm going to pause the video now. And I'm back. Check your notation, check your graph. Should look something like this. Is the function f continuous at c? Nope, got a hole again. So no, once more. All right, what does it take? What does it take to be continuous, right? Here's the last two pieces of information for case number 6. First one is that f of c is equal to L. And the second is that the limit as x approaches c of f of x equals L. All right, I will pause the video now. All right, I'm back. How did you do? Does your graph look nothing like this at all? Which is fine, but does it actually flow through at x equals c without having to lift up your pencil? Yes. So is this function continuous? It is, yes, continuous. I'll even spell it out. Continuous at x equals c. Maybe we should say f is continuous at x equals c. All right, so what does it take for there to be continuity at a point? Well, we're going to go over to this side and we're going to write it all out. So this is actually the definition of continuity. Continuity at a point. A function f is continuous at c when these three conditions are met. The first condition has to be that f of c is defined. So you actually have to have a point. So is defined. So you could also state that c is in the domain of f. And just being in the domain means that it produces an output value, a real number output value. Okay, I forgot f. Okay, the second piece of information that has to be true is that the limit as x approaches c from both sides of f of x has to exist. So it exists. And the last piece of information puts these two together. Not only do these things have to exist, they actually have to equal each other. So the limit, when you approach c, when x approaches c from both sides of f of x, has to actually approach the value of f of c so that they all match up and you have a nice continuous flow. Okay, so we will, these are actually conditions that you must memorize to prove continuity at a point. So here's some examples of discontinuity. Discontinuity basically means at point C, it's discontinuous. So another way of saying not continuous is discontinuous. So here we have a hole, here we have a break, and then here's another hole, right? Three conditions that have to be met. So on this one right here, f of c is not defined. Here it is defined, but the limit doesn't equal. Here f of c is defined, but the limit doesn't go to that. So these are the cases that do not meet the conditions up above. Okay, so we're going to go through and determine continuity at each of the following x values listed. using the graph right here. So let me read this more specifically. Determine whether the function f is continuous at each indicated value of x, and if not, state which condition of continuity is not met. So looking over at x equals 1, here's x equals 1, you can see that, first of all, the limit exists, but where's the point? There is no point associated with, so you're going to say f of 1 is not defined, which basically means there's no output value for 1 in the function f. So that means f of, or f, don't say f of, say f is not continuous at x equals 1. Okay, what about at x equals 2? So we're going to go over here. There's 2. We see that there is a point associated with it. The limit does exist. The problem being they are not equal to each other. So you can say f is not continuous, I'm going to abbreviate, at x equals 2. Why? What condition is not met? Because f of 2, which is actually equal to 3, does not equal the limit as x approaches 2 from both sides of f of x, which actually equals, what does it equal? 1. So they are not equal to each other. So that's how you would answer this question. Okay, moving on. Let's go ahead and take a look at this one. We're supposed to determine whether this function is continuous at x equals 1. So what I'm going to do is I'm going to allow you to kind of figure that out. You see that this is a rational function. I'd like you to try to think back on your pre-calculus and do a little bit of investigation at x equals 1 and see what you come up with. I'm going to go ahead and pause the video, and you should as well, to complete your work and then come back and check it. Okay, I'm pausing the video now. Okay, so one of the first things you probably tried is to see what the value of the function f is at 1, and it comes out to be that you create division by 0, which means you have a vertical asymptote, and therefore f of 1 is not defined, and that's all you really need to know to prove that f is not continuous at x equals 1. Okay, video 1 is over. You can continue on to video 2.